So, any questions? Anybody do the 4 homework problems I assigned? You did one of them? Read the section, did one of them? Okay.
Worked through a couple, and then I did number 83.
Okay. How'd it go?
Took a long time.
Took a long time. All right.
But
But you got there.
yeah.
Okay. Anyone else?
Time to do all.
Not to completion.
Not to completion. Okay. You're doing chemistry. Okay. So no questions then. All right. I'm moving on. Oh, you do have a question.
So I found a different problem online because I couldn't find it.
That's fine.
And it shows like.
Can I see your paper?
Yeah. Basically, it shows like a table.
Yep.
With.
Yeah.
Like a.
Sure. Can I borrow it for a sec?
Yeah. And it has. Like multiple 3/4 numbers, and I was like, okay, so how do we.
Okay.
Find it? That's funny where I start.
All right. So go ahead and start writing in your notes. This is engineering. I'm starting to think it was world religion. Okay. And what do we have? Okay. This is a great problem. Thanks for doing it. Okay. So I assume we're asked to find, what are we asked, what are we looking for actually? Like the reactions. Okay. So let's try and find what's going on here. You know, if let's say this is on a skating rink, so it's on a smooth surface. Okay. That means that there's going to be some AY and BY, right? Any other reactions? Okay. Looking at this, we can automatically tell what AY and BY are going to be, right? 50, right? They're going to be 50. Okay, so they're 50 each. Okay. Maybe we want to look at DCB and ACE, right, and figure out what's going on with each of them. Does that seem reasonable? If these were not pin connected, would this be in static equilibrium at C? If there was no pin at C, what would happen? It would collapse, right? So there's some loads at C. So maybe what we're trying to figure out is what are the loads that are happening at C, right? So I'm guessing the question asks something like find the reactions at the pin at C, okay? So if we know these, we need to draw some free body diagrams, right? So we could draw a free body diagram of DE. Okay. And that means that at E we'll have some EY and some EX. And at D we'll have some DY, DX. Right? Looks like we have 4 unknowns. Okay, we could solve for dy and EY. Right? What are they going to be equal to? 50. Okay. We actually don't know that dx and ex are 0, and they're not 0. Okay, so we do know that we could write the equation sum of the forces in the x equals 0, and that would have dx plus ex equals 0. Right? But we can't say that they are equal to 0. We can just say the sum of them is equal to 0. Okay? All right, so we have two unknowns still that we need to solve for. Let's look at DCB. Okay. So we know that at B, there's 50 pounds up. At C, I'm going to have some CY and CX. What's going on at D? There's 50 pounds up?
Or cut down.
There we go. There's 50 pounds down because it's opposite. And there's some dx to the left. Right? Now, how many unknowns do we have here? 3. Okay, so we should be able to solve this. Let's give it a whirl. Okay. So sum of the forces in the x equals 0. I'm going to draw a line across here just so that you see that one went with that one. So in the x, it looks like I'll have negative dx plus cx equals 0. Well, that's not awesome. Sum of the forces in the y. Looks like I have negative 50 plus 50 plus cy equals 0. Right? So cy is 0. Okay. All right, now let's sum our moments. Where do you want to sum the moments about? Okay, let's sum them about C. Counterclockwise is positive. So if I sum about C, it looks like I'll have 50 times 1 foot for this guy, right? Because I pin it here, that's counterclockwise, so that means it's positive. How about this 50? Pin it there, push it up, we get the clockwise rotation. Counterclockwise, excuse me. So I have plus another 50 times 1. dx, so plus dx. Its lever arm here is 1.5. And I think that equals 0. So we have 100 is equal to negative dx times 1.5, or dx is equal to 100 over 1.5. Is that 66? Okay. Did you ask how I did that? Because I think what times 1.5 equals 100. And so I was able to think, oh, let's see. Yeah. Okay. All right. So now we have dx. So we can substitute then dx up here. And we find that negative 66.7 is dx. So that becomes a negative 66.7 plus cx equals 0. So it looks like cx is equal to negative 66.7. Right? No, it's not, because we drove, we didn't drive anywhere. We drew dx as if it were going to the right, so meaning that it's compressive on this member DE. Is that what would be happening though? If you think about it, our table is hinged in the middle like an X, right? And so when you put a weight on the top, it's trying to do this, right? It's trying to collapse down. So that means that D and E, which are my dirty fingernails there, are trying to get further apart from each other, right? So they're putting DE in tension, and so DX should actually be in that direction, right? So I'm okay, I'm relieved actually to get a negative 66.7 for DX because it's telling us it's going the other way.
I was looking at how it's going that way, and then it's negative on the other.
Oh, on this one?
Yeah.
Yes, so same idea here. We know that this is in tension, so when it's interacting with this, it's going to be pulling on D, right? So really the load that's there is going on member DCB should be pulling it into the middle, right? Equal and opposite works out, okay? Joseph, does this answer your question, Hannah? Okay, so you also could have done this by looking at the other member, right? You could have looked at ECA. It would be pretty much the exact same process. There is a trick here. What was the trick? Where could you have gone wrong and not have been able to solve this? At D, right? Because we started with DE, and when we did that, we established a dy dx, right? And then when we move to the next member, we need to remember that we have to flip it, that they're equal and opposite at points of interaction. Okay? So if you hadn't done that, you'd be up a creek. Okay? So you need to make sure that where it interacts with a pin joint, their forces are equal and opposite in the free body diagrams. Okay? Got it? All right, let's move on. We're going to start talking about chapter 7. Which is all about internal forces. Okay. I'll give you a chapter 6 problem to start with. All right, here's our bridge. Okay. And maybe we put a couple loads on this. Okay. And maybe I say, well, I want to know what's going on with this guy right here. Right? How do we solve this problem? Sections, right? We could do it method of joints, but method of sections is a lot easier. So we're saying we want to find, we can figure out, we can look at it, it's not symmetric how I drew it, but assuming that it's actually built symmetric, we would know, okay, the reactions here are 1,000 up at each of these points, right? If it were symmetric, okay? But then if we want to know anything about what's going on inside of the truss, what one of the loads in the members is, we have to cut it, right? So we'd cut that thing so that it goes through three members, and then we'd put our unknowns on it and we'd solve. Okay? This is because this is a rigid body that's made up of a bunch of two-force members, so we know the directions of those forces. In engineering, we certainly build bridges that are made up of entirely of two-force members, but it's also super common for us to use beams. So maybe instead of a nice truss bridge, maybe instead of that, I just use a beam. Okay? You used a beam? Great. All right, so if we put a beam, and maybe we'll put the same loads on it. 1,000 and 1,000, right? We can solve for the reactions. 1,000 and 1,000. But how do we know if that beam is going to break or not? What do you think makes the difference in whether the beam breaks or not? I'm glad you're here today, Brandon. Brandon says internal forces. Perhaps, right? But I mean, think, besides just regurgitating the words that have come out of my mouth recently, how about what makes a difference? What makes a beam break or not break? The strength of the materials, okay, but what else? Lance, you said something? The length of it, sure. There's lots of things that we don't know here, like the length. Okay, what else? Where the force is applied, yeah. How far is this, right? Because, Liana, in your experience, would you be able to carry more load as it gets further away from the support or less? Less, right? So if I could put this closer and closer here, it might make a difference. Now, what you're talking about there is actually failing due to bending, okay? And that has to do with the fact, what is it when we put a force further away from a point? What's that change?
The moment.
Changes the moment, right? It doesn't change the reaction here, right? The reaction here doesn't change whether this 1,000 pounds, like let's make it simple. Let's eliminate this guy and say there's just this 1,000 pounds that I can move back and forth, okay? Does moving this anywhere on the beam change the reaction here? It does, yeah. The force reaction. At the pin, it changes the force reaction, right? Because if I put it all right here, it's all going to be 1,000 pounds, and this will be 0 over here, right? If I put it in the middle, it'll be 500 and 500, okay? So we've got length, we've got position of the load. What else about the beam will tell us whether it's going to break or not? Say you try something and the beam breaks. What would you change? Okay, you could change the material, right? Instead of making it out of spaghetti, you could make it out of steel, right? Or a popsicle stick, okay? So maybe the material, let's say that you have a popsicle stick bridge or beam, and it breaks. Now what are you going to do? What are you going to change now? What's that? Something thicker, right? So you're gonna add thickness to the beam. You're going to change the shape of the beam. What about if we're looking straight on at the beam? If you use a popsicle for this, right, and you lay it this way versus laying it this way, right? So I'm saying we're looking straight down the beam here. Does it make a difference which way I lay the popsicle? Yeah, it makes a huge difference, right? Which one of these is stiffer? The vertical one is much stiffer, right? This guy's much bendier. So I should have brought a popsicle stick. Shame on me. Yeah, I could use a yardstick, but I don't see it. It's usually around here for hitting students with. It's all right. Okay. So what we need to do in order to determine, and this is kind of getting a little bit into what strength of materials is about, is strength of materials is as much strength of materials as it is strength of shapes. Okay? So in strength of materials, we say, why is this flat is this short, wide shape, much less stiff than this tall, skinny shape. Okay? So that has nothing to do with whether this is spaghetti or titanium. This shape, no matter the material, will always be less stiff than this shape of the same material. Why? What's what called? That concept? Yeah, so it has to do with what's called the area moment of inertia. But that's not what we're talking about today. Okay? What we want to talk about is, forget the shapes, what about the forces that are going on here? How do I determine what the load is inside of this beam? And wouldn't you know it, when we needed to find the load inside of the bridge, we cut it open. We're going to do the same thing with the beam. We cut it open. Okay? And we draw the two free body diagrams. Okay? Now when we cut open the bridge, remember I said if you cut it open, it's going to bleed. There's some unknowns there. So we need to put some loads on the cut. All right? There are 3 loads that we need to put on a cut when we do this. The first is the normal load. It always comes out from the cut. Okay? That's nice because it makes it that when we go to the other side, what do you know? It's equal and opposite. Right? So there is an equal and opposite force pair here because we're saying that both sides of this are in static equilibrium. Right? So what we're trying to do is, remember in method of sections, what we are predicating that on is that this bridge is in static equilibrium. So we can say that the sum of the forces is equal to 0 and the sum of the moments about a point is equal to 0. And then we determine the unknown internal forces that make that possible. Okay? Same thing here. This beam, we're saying, is in static equilibrium. So we can cut it open, and then we need to determine the unknown forces needed for it to be in equilibrium. In this case, what would the normal force be? 0. Why, Lance? Yeah, there's nothing acting in the x direction. So when we did sum of the forces in the x, we're going to get sum of the forces is equal to n, which is equal to 0. Okay? All right, so that's the normal force. It always goes normal to the face of the cut. Okay? The next force is V, and it's the shear force. Okay? And the way we draw V is always so that it causes a clockwise rotation of the beam. Okay? So in this case, drawing V down would cause the beam to rotate clockwise. Okay? And then on the other side, I'd have to draw V up, again, so that it causes clockwise rotation. We get a force pair there. The two V's are equal and opposite in direction. Okay? It's the shear force. V is the shear force. Okay? What is the shear force? Okay, so if we look at it, the shear force is the internal force that's keeping the beam from slipping against itself like this, right? So we're used to thinking, like if we think about shear, a shear force is like a sliding force. So if I'm going to shear two things apart, I'm going to slide them kind of like this, right? So that's kind of what we're doing with the face of the beam here, is that we're sliding the beam face like that, right? So it's causing two planes to slip against each other, okay? So that's a shear force, whereas a normal force causes the two planes to pull apart from each other, right? So it has everything to do with the direction of the force compared to the face that it's acting on. Does that make sense? Okay? So shear is, you can always think of it as sliding, and normal is pulling apart. Okay? Would those be acting on the same point? Great question. So right now, we are kind of taking a simplified approach to this, and we're not considering the cross-sectional area of the beam, right? So we're saying that the total shear that is supported by that face is this, right? In strength of materials, we'll explore that actually the shear does vary as you go through the cross-section of the beam. But for now, all we're finding is the total. Does that make sense? Okay? And same with the normal, actually, right? That the normal varies, but we're going to just go with the total. Okay? The last force we need to put on this, or last unknown, I should say, is the bending moment. Okay? There's 3. Okay? $3 is not a lot, right? 3 unknowns, not a lot. Okay? So, how do you decide which way to put the moment? Okay, so how do we decide what positive is? So we're going to say that a positive moment causes a beam to be concave up. What that means is that a positive moment, when it acts on a beam, causes it to be concave up like this. And I prefer, that's kind of hard to remember, I think positive moments cause happy faces, right? If there's a lot of positive moments in my life, I'm going to be smiling. That's smiley.
That's really good. You put that on the shirt.
Positive moments cause smiles? Or which piece should I put on the shirt? All of it. Yes, Jason. Yeah, so the question is, did I arbitrarily pick the direction of the shear? No. The direction of the shear is based on making the beam or the section I'm evaluating rotate clockwise. So on the left-hand side, putting the shear down would cause the beam to rotate clockwise. On the right-hand side, putting the shear up causes the beam, if it doesn't roll, to rotate clockwise. That makes sense? Let me try it that way. There we go. Okay? All right, so what about the moment on the other side then? Which way would bending this cause it to smile? Up and to the right, which you see that these are equal and opposite, right? So we know that if I sum the forces and moments on both faces, they all are going to go to 0 because the normals are equal and opposite, the shears are equal and opposite, and the moments are equal and opposite. Okay, so that's what we want. Now, we solve for these just like we did the method of sections, right? So we only have to solve one side, and we have the answer for the other side. Okay, so let's go ahead. I'm going to redraw the left-hand side because I always like to start on the left-hand side unless there's a really good reason not to.
So we don't use the right-hand rule anymore for moments?
We actually, so the question is, we don't use the right-hand rule anymore for moment. We still do, actually. This is a positive moment because it's going perpendicular out of the page. And we're saying that if x and y are here, x and y would be, z would be coming straight out of the page. So this is following the right-hand rule.
What about the right side?
Yeah, forget about it. Yeah, on the right side, we're saying that a positive moment causes the beam to be concave up, and that this would be the direction of the moment here. Okay. All right, so then I've got 1,000 down. I have the normal. I have the shear. And I have the moment. So to solve these internal loads, sum of the forces in the x is equal to 0. Okay? This way is positive. The only thing I have acting in that direction is the normal, so it's equal to 0. Sum of the forces in the y is equal to 0. So I have 1,000 up, I have 1,000 down, and I have v down. So notice that v has a negative sign in front of it here, but I said that positive shear in this case is down, right? That's okay. I'm saying the value for the shear, I'm calling it positive if it causes clockwise rotation of the face of the beam, okay? But it's acting down, so if I'm saying that up is positive when I'm summing the forces in the y, I have to put a negative sign in front of it, okay? So when I said, if I asked you maybe to plot the shear, you would plot whatever we determine here. Well, I mean, we can look at this and see that v is equal to 0. Let's say v was equal to 100, okay? That it was 100 down. If I ask you to plot me the shear as we go across the beam, which I am going to do, that would be above the x-axis because we're saying that's a positive shear. Even though it's going down, we're saying that's positive because it would cause clockwise rotation of that segment of the beam. Okay? And let's sum our moments. And when we do this, we always sum the moments about the cut face. All right? Always sum the moments about the cut face. You can sum them other places, but always sum them about the cut face. All right? It makes it so that we're all on the same page and that it works better. So sum the moments about the cut face. All right? So here, I guess I'm going to have to give us some numbers if we want to solve this. Let's say that this is 5 and this is 2.5. Okay? So if I sum the moments about the cut face, I'm going to have the moment, right, because I'm saying that's my unknown. Counterclockwise is positive. It's counterclockwise, so that's good. Plus 1,000 times 2.5 minus 1,000 times 7.5. Okay? And all that has to equal 0. So it looks like it's 2,500 minus 7,500. So 0 is equal to the moment minus 5,000. Okay? So the moment is equal to 5,000 whatever units we're talking about. Foot pounds, Newton meters. Okay? So what I'm trying to show you here is that you've got method of sections, right? Easy peasy lemon squeezy. Solve for the reactions, slice it open. Internal forces is the exact same thing. Solve for the reactions and slice it open. The only thing you have to be careful of is that you follow our sign conventions or our conventions for establishing which direction is positive for the unknowns. Okay? So let's do some examples of this. Because it's an unknown that we put in. So the question was, why do we add m into this analysis? Why is there an m right here? At least I think that's what the question is. Why is there an m right here? Is that right? Yeah, because when we cut it open, there's some internal moment there, right, that we have to account for. So it's an unknown. Okay? All right, so let's try a couple of these. Okay? So we have a beam, has one force on it. Okay? Force is at a 3, 4, 5 angle. And let me zoom in. I see some squinting. Is that better? That is a 2 next to the E. So I'm saying the E is 2 to the right of A. Okay? And I guess these are all feet, right? Because we're... All right? And I'm going to ask you, I'm going to zoom back out a little bit if that's all right, if you got it in your notes. So. Here's what I'd ask you. Find internal loads at D and E. Okay? So I'll do E with you, and then I'm going to have you do D at your table. Okay? What's our first step? What was our first step in method of sections? Nope. Solve for the reactions, right? So we need to know what's going on at A and what's going on at C. All right? So I'm just going to kind of, this is reactions that we're solving for. So some of the forces in the X has to equal 0. My unknowns looks like I have some AY, some AX, and some CY, right? So I have AX plus 3/5 of 350 equals 0. So it looks like AX, I think that's negative 210. Okay. Some of the forces in the Y. Okay. So in the Y, it looks like I'll have AY plus CY minus 4/5 times 350 equals 0. Can't solve that guy yet. So let's sum our moments. I'm going to choose to sum my moments about B. Why am I choosing that, you think? What's that? Because there's no trig? Yeah. Okay. Not that the trig here is very hard, right? They're similar triangles. But we'll sum them about B. Looks like I'll have negative AY times 3 feet plus CY times 7 feet equals 0. So actually, it probably would have been better to sum the moments about A or C. Right? Because now I have to solve my simultaneous equations. If I summed my moments about A or C, I could just solve right away for it. Okay? Could somebody calculate this for me? So I think AY is going to be 196, 196 pounds. And I think CY is going to be 84 pounds. I haven't, that's me shortcutting and hoping I'm right, so please check it.
I got AY 196 and CY 84.
Yep. Okay. All right, so now we know something about our beam. What do we need to do next? We're going to start at E. Cut it and draw a free body diagram, right? So we're going to cut it at E. Okay. We put on our known loads, which is 196 up and 210 to the left. And then we put on our unknowns. Who can help me with an unknown? A normal going to the right. Why is it going to the right? Because it always comes out of the cut face, right? Why is V going down? To make this member rotate clockwise. Okay. Counterclockwise moment to make it a happy beam, right? Positive moments cause happy faces. Okay. All right, so now we're applying these same equations we've been doing for weeks now, probably a month, right? Sum of the forces in the x equals 0. So it looks like I've got negative 210 plus the normal is equal to 0. So the normal is equal to 210 pounds. Sum of the forces in the y has to equal 0. I have 196 minus v equals 0. V is equal to 196 pounds. Excuse me? Great question. What happened to our 350 pounds? I sectioned it at E, so the 350 pounds is on the right-hand side. And I'm looking at the left-hand side. Excellent question. Okay? Yep. So the question is, when I take the section, I'm cutting straight through E, and that's correct. Okay. I could, I suppose, cut at a diagonal through E, right? And then my normal would be perpendicular to that diagonal. My shear would be along the face of the diagonal, and the moment would still be to cause a happy beam. The question is, why would you do that? If the book asks you to. So it'd be so annoying, but actually one of the good reasons you might do that is maybe you have your beams made out of a composite that's made up of stacking things at an angle, right? So you want to know the shear force along that plane, and you want to know the normal force to figure out if it's going to fail. That could be one reason, right? For now, we're going to be nice and use steel, okay, which is an isotropic material, meaning it's the same in all directions. Last equation, sum the moments. Where do I sum the moments about? Yep, the cut or the face. So I always put a little c on it, say that's equal to 0. Counterclockwise is positive. So I'm summing about this point right here. So I have that eliminates shear and it eliminates the normal. And then I'm left with the moment at E, I guess. And that's in the positive direction, minus 196 times 2 equals 0. So it looks to me like the moment at E is going to be 392 foot-pounds.
Why'd you do it around
The cut. C stands for the cut.
Oh.
You always do it about the cut because what it does is it eliminates the shear and the normal unknowns, and you can solve for it directly most of the time.
You said you were doing it around point C.
Ah, I'm sorry, yeah, I'll put a UT on this. Moment about the cut, not about point C. Okay? That process make pretty decent sense? These three unknowns are the internal forces at E. Yep, that's exactly right. Nope, so this moment, good question. The question is, that moment's for throughout the whole thing. No, this moment is just at this point. The internal bending moment is just at point E. But so I guess it's the whole face at E. Yeah, but it's not, do you think it might be different at B? It might be different at D. Okay? So what I want you to do now is I would like you to find the internal forces and bending moment at D. Okay? I'm going to tell you right off the bat, there's an easy way and a hard way to do this. Okay? So go ahead and slice the beam at D, put your unknowns on it, and solve. Okay? So I'll give you 10 minutes to do that at your table. D. All right, how we doing? You able to solve it? Do you feel like you did the hard way or the easy way? Okay. We're going to find out. How many people think they did the easy way? 5 people. 6. Okay. So, Brandon, if you did it the easy way, what's your free body diagram look like? It's a block. Awesome. Is it DC or is it AD? It's DC. So Brandon solved this by drawing the right-hand side, right? Where then you had, what was this, 84 pounds up. And at D, you had a normal going which way? Out, right? Shear? Up. And moment? Clockwise. Okay? Did anyone do the opposite side? Nobody? I didn't snooker anybody into doing it from the left-hand side. All right, this is the easy way, okay? We will also solve it the hard way so that you can see how that works. So sum of the forces in the x has to be equal to 0. Well, it looks like we just have the normal. Huh. 0. So up above, the normal was 210 pounds, and here we find that the normal is 0. Why is that? Well, if we think about it, the force is pulling and push, or is pushing at B, right? It's pushing it to the right. What keeps that from going to the right? Is it anything to do with C? No, it's this pin. It's AX that keeps this from moving to the right. So internally, there's no stress here. There's no load that's keeping this from moving here. So there's no normal load. It's all taken care of over here at AX. Okay? So the normal is equal to 0. Let's do some of the forces in the Y. Up is positive. So it looks like I have 84 pounds plus V equals 0. So V is equal to negative 84 pounds. So we have negative 84 pounds of shear. What did we have above? Above we had 196 pounds of shear. Huh. The other forces are what? Because of this force acting? The 196 right here? Could be. Some of the moments about where? And clockwise or counterclockwise is positive? Counter. Joseph's got it. When I do my summation equation, I always say that counterclockwise is positive. Now the moment here, that's going to be negative. Right? And that's the moment at D. So negative the moment at D, it looks like plus 84 times 3 equals 0. So the moment at D is 252 foot-pounds. Okay? That's the easy way. Hard way would look like this. Right? Look at the left-hand side of the beam. We have to put the reactions and the load on it. Sum of the forces in the X. Well, it looks like I'll have negative 210 plus 3/5 of 350 plus the normal equals 0. This is 210, so we find normal equals 0. Sum of the forces in the Y of 196 minus 4/5 times 350 minus V equals 0. 4/5 of 350 is 280. So it looks like negative 84 minus V equals 0, or V is equal to negative 84 pounds. That matches that, right? That's good. Sum of the moments about to cut. I'll have negative 196 times 7, right? Because if we go back up here, I'm cutting at D, which is 3 from the end, and it's 10 long, so that makes it 7 from A. um, plus 280, which is the 4/5 of 350. That's the vertical component here. Times the distance to that, if it's 7 long, 3 be 4. Is that right? The distance from D to B is 4, I believe. Okay. Plus the internal bending moment at D equals 0. I don't want to do that in my head. Can someone do that? I really hope that it gives us 252 foot-pounds. Okay. So either going left or right, we get the same answers. Okay. How you feel about this? Good? Awesome. Okay. Internal loads at B. I'll pause it again and give you 10 minutes to work this. So hopefully you come up with something like this. Solve for the reactions is a first step. We find out that CY is 112.5 and AY is actually going down with 37.5 because this weight's going to cause it to want to go up, so AY actually has to hold it down. Excuse me? Yes, sir, it would be. MB would be negative. Okay. So once we find those reactions, then we slice it where we're interested in. We can choose either the left or the right. In this case, I chose the left. And write my force summation equations. Okay.
So you sum the moment around the cut, but then wouldn't that mean you also ignore the moments? Like, how are you also finding moments at the cut from?
Great question. So Joseph's asking, so if you're summing the moments about the cut, why are you still considering this internal moment? Am I understanding your question correctly? Yeah, because this internal moment is like a couple moment. Okay, so it doesn't cause any change in the forces. And so it doesn't matter that it's applied right at the face. We still account for it because it is a moment that causes twist right there. Okay, so you do need to account for this because it's a couple moment. And so you don't account for the shear and the normal because they have no lever arm, right? They're just a single force with no distance. The moment here is a couple moment, meaning that it's a combination of two forces that are doing this, okay? And in fact, what we'll find, Joseph, as we go on, when we start to look at this, what we'll do in strength of materials, if we look at this face, right, and we come up with the fact that we have negative 93.75 foot-pounds, right? So what that's telling us is that we have 93.75 like this. This bending moment is what this is called. This bending moment results in a stress distribution across this face where below what we call the neutral axis, which if it's symmetric is smack dab in the middle, it causes a compressive force, and above it, it would be causing a tensile force. Okay, because in these, what happens is that all of these forces that are normal here create the couple moment of 93.75. So there's actually an internal normal force at the top here that's going this way, and at the bottom that's going this way, and they form a couple that has a magnitude of 93.75. Does that make sense? Yeah. Okay. It's called the bending moment because it's what's caused by when we bend this thing, or a beam, not this one, but when we bend a beam like this, right, the top of that beam actually shrinks, the bottom gets longer, right? And so that's those compressive and tensile loads causing that to happen. But it's just this twisting, that's how the loads are kind of converted from being a twisty force to being linear forces that are separated by a distance. Okay, great question. And a little bit the answer is you're going to have to wait until strength of materials to fully understand that. But for now, suffice to say that it's a couple moment, and therefore we have to account for it because it doesn't matter where it's applied. Okay. So why are we doing this? We're doing this because we often need to size our beams, right, such that they don't fail. That's typically the goal, right, is to make a beam so that it doesn't fail. And we know the external loads on it. But to figure out whether it will fail or not, we need to know what the internal loads, what the shear stress is, and what the bending moment is. Because beams, we can say, typically have two common failure modes. Failure due to bending and failure due to shear. Okay? And so what we're going to need to do is to figure out, okay, as I go across this beam, where is its maximum bending moment? Where is its maximum shear value? Okay? And that will help me to size the beam appropriately. That means if we're using like a wood beam that's a constant cross section, we're probably oversizing it for shear in many parts of it, but we want to size it appropriately for the part that has the highest amount of shear. Right? We're designing for the worst spot in the beam. That means some parts of the beam it's gonna be not even close to failing, where this one it's the closest. Does that make sense? Okay, so where we're gonna go on Friday is we're gonna transition from finding it at a point to turning this into a function. So that as we go from A to the other end of the beam, what does the shear look like? What does the bending moment look like, right? So right now we're just finding it at a point. 7.2, we're finding it as a function of x as we go from left to right across the beam. What are those values? Okay, so go ahead and read 7.2. That's what we're going to be covering on Friday. Okay, I am going to, based on how far we got today, I'll post a graded problem today that will be due on Wednesday because we don't have class on Monday, right? We don't have class on Monday. It's Veterans Day. Okay? So your graded problem will be due on Wednesday, and we will have our quiz on Wednesday. So just because we're not here on Monday doesn't mean you get off with no quiz next week. All right? Cool.